Everybody likes to argue what 0 to the 0th power is, but nobody ever talks about what 0 to the 0 to the 0 power is. So today, let's focus on this limit in particular. We have x, y, z approaching 0, 0, 0, and then we have x to the y to the z's power. And whenever we have a power tower like this, it's meant to be y to the z's power first, and then we do z to that power. Okay, so I will tell you though, this limit right here does not exist. To do so, we have to come up with two different paths, and they give us two different results for the limit, and then we'll be done. So how do we do it? Firstly, I'm just going to say with the usual one, let's just say x is equal to y, it's equal to z, and let's call it t. So I'm going to use a new parameter right here. So they are approaching the origin, right? The same thing. And by the way, this right here, technically it's all 0 plus. Just keep that in mind, because if you have negative number here for the base, if this right here is a rational power, well, you get imaginary result. That's not good. But anyway, this right here becomes just t approaching 0 plus, and then they will all be t's. So t to the t to the t, like this. Along this path, which is just a diagonal, right? Just think about it as a diagonal. This right here will give us 0. And to do so, what we will do is, we will do the limit of this thing first, and then we do this base to that limit. Have a look. We will get the limit of t approaching 0 plus of the base t like this, and then we focus on the limit as t approaching 0 plus of this power, which is t to the t. And for this right here, I do have to do it on the side. So I'll just say it right here. If you plug in 0 into here, you get 0 to the 0th power. That's a no-go because it's indeterminate. We like to use base e. So let's look at this as the limit as t approaching 0 plus. Put this t as e to the ln t, and then raise that to the t's power. We can multiply the exponents. So we multiply this t right here. So now we will have e, this is 0, ln 0 plus is negative infinity. So what we can do is bring this t down. So we look at this as the limit as t going to 0 plus base e ln t over 1 over t. That way, right here we get 0 on the top, and then infinity, negative infinity on the top, and then positive infinity on the bottom. Either way, we can still use L'Hopital's rule, right? The negative doesn't matter. So go ahead and differentiate that, d dt, d dt. So this becomes the limit as t approaching 0 plus e on the top is 1 over t, on the bottom is negative 1 over t squared. And then just work this out real quick. So it's the limit. I'm just trying to show all the work. I know this answer is equal to 1. You guys should know that too, because it's a famous question. But anyways, e to the negative, and then that's just t. And now plugging 0 plus is e to the negative 0. Doesn't really matter. It's just equal to 1. Okay, this right here is 1. So what we get is, this right here is the limit as t approaching 0 plus of t, right? That, and then the exponent is 1. That's just 0. 0 to the first power, of course, is just equal to 0. So for our first path, this limit is equal to 0. Now, we have to come with a different path that it's not going to give us 0, so we can say this limit right here does not exist. Now, this is a hard case, because we have to find a path so that x, y, and z, they approach 0 individually, and also because the base will be 0, and if this thing right here do not approach 0, such as what we have found earlier, well, we will end up with 0 to a non-zero power that will give us 0 guaranteed. which will end up with the same result as the first path, and that's not good to show this limit does not exist. Therefore, we have to think about something so that this thing is in the form of 0 to the 0's power, and the result is 0. But 0 to that 0 power does not give us 0 at the very end. So how can we do it? Well, this is the fun part. In fact, I did 2 videos before showing you guys 0 to the 0's power could be approaching 0. Here we go. This is the path that I'm going to use. I'm going to write z in terms of y, and later on I'll just use y as the variable. Okay, along the path that z equals. Later on we have y to the z's power, right? Keep that in mind. I want to have this thing approaching 0, and I will use 1 over ln y. For now, you'll see. Because my idea is if you put 0 plus in here, you will get 1 over negative infinity, which is going to be 0, right? When y is approaching 0 plus, we get this. And if you have y to the 1 over ln y power, in fact, you just get e. That's not approaching 0. That's not what we want, because if that thing approach e, then we get 0 to e's power, you get 0. So I need to make this result even smaller 0. So how I do it is this. I want to put another ln. But if I put another ln here, this thing on the inside is negative infinity. ln of negative infinity doesn't make sense. It's okay. Now negate that. So force this to be positive infinity, and then do another ln like this. So that will be 1 over infinity, which is approaching 0. This is going to work. And now I'll just compute the limit as y approaching 0 plus. This is y, and then we want it to raise to the z's power, which we said is this. That's 1 over ln of negative ln y. Okay, to do this, we don't like to have base y, we like to have base e. So do the usual business. The limit y approaching 0 plus, that is e to the ln y power. And then multiply by this, which I will just write as over ln of negative ln y. And then do L'Hopital's rule here real quick. You will get the limit as y approaching 0 plus e. On the top, you get 1 over y. On the bottom, the derivative ln is 1 over the inside, but you multiply by the derivative right here because of the chain rule. So it's negative 1 over y. Cancel, cancel. Negative and negative is positive. Put the ln y up. So this is the limit as y approaching 0 plus of e to the positive ln y power. And in fact, you can see they cancel out nicely, which is really nice. Yeah. And yeah, this is just going to be 0 because they actually just cancel. You can make it so that they don't cancel. You can say maybe put like a little 2. I think that will work as well, but they cancel out very nicely. So anyways, okay, so y to the z's power give us 0. Now we have to think about what x is. So I have to define x. I will do base e because it's nice. You can also use 2, doesn't really matter though. And then I will do 1 over y to the z's power. And negative. So let me just first double check that if x will be approaching 0 as well. So y to the z, just like what we have earlier, it's going to be approaching 0. So this is going to be e to the negative 1 over 0. And technically it will be 0 plus. So this thing right here becomes e to the negative infinity's power, and that will be approaching 0. So x, it will be approaching 0. So now what's happening is this. This is my z, and y is just y, and this is my x. So ladies and gentlemen, I'm just going to say the limit, and everything's based on y, so y approaching 0. X is this, which is e to the negative 1 over y to the z's power. raise that to the y's power and then the z's power, which is, I'm just going to write it like this. This thing right here is approaching 0 as I showed you guys earlier, but the good thing is, right here, right now, we can do what? Multiply the exponents. So this right here becomes the limit as y approaching 0 plus. You just get e to the negative 1, which of course is just 1 over e. Yeah, and of course now you can see that they have different limits. So you can come back here and say this limit does not exist. Yeah, that's it.